Good morning, students. So in today's class we are going to continue the concepts that we are left with, realization of the filter. So in that we'll do one problem. So in the question they said realize the system of the function h of z is given 1 by 2 1 by 3 z power minus 1 plus z power minus 2 plus 1 by 4 z power minus 3 plus z power minus 4 1 by 3 z power minus 5 plus 1 by 2 z power minus 6. So this is the given function. We need to find that particular function, that is called realization of that function by using the realization of type 1, type 2, cascaded form. These things we already covered, so we are doing the continuation of the same problem by doing the realization of the function. In order to proceed with this problem, we know the linear phase filter. So what is a linear phase filter? What's the meaning of linear phase filter? So to find the linear phase filter, h of n is equals to h of n minus 1 minus n, right? What is n? N indicates number of samples. Small n is what? Given whatever the numbers they gave, the index value. So we had h of n is equals to h of capital N minus 1 minus n. This is the way we will have to go for realizing the function. So what actually the thing is z power minus 1, z power minus 2, z power minus 3, so on till z power minus 6. So first thing, we need to go for the summation part and then the factor of z power minus 1. So these factors we need to segregate and we need to keep on multiplying with the given function. So the meaning is that whenever we do have these kind of questions, first criteria is to find the linear phase of this particular response. So in order to do that particular response, what we are doing, we are giving first h of z, we will try to modify it by x of z by y of z. That form we need to write. After writing that form, we'll try to multiply with z factor. Okay, so what we need to do it, we need to write the transfer function, right? What is h of z? What is h of z? I can write h of z is y of z by x of z, right? That's equals to, what is the given factor we do have? 1 by 2 plus 1 by 3 z power minus 1 plus z power minus 2 1 by 4 z power minus 3 z power minus 4 1 by 3 z power minus 5 plus 1 by 2 z power minus 6. So next criteria is that we just want to multiply with x of z so that we can get the output response. So y of z is equals to x of z with 1 by 2 plus 1 by 3 z power minus 1 x of z plus z power minus 2 x of z 1 by 4 z power minus 3 x of z. So 1 by 3 z power minus 5 into x of z plus 1 by 2 z power minus 6 into x of z. So what we did, we try to find y of z. What is y of z? This is the actual output response. So we need to get the output response for it. So we need to get that particular factor. So we multiplied the transfer function. This is what? Transfer h of z. So impulse response of the h of z, we wrote it output by input. So this input value we multiplied. Next criteria is to design it. For designing these things, what is required in that? We need to multiply the coefficients value. We do have these all coefficients value. Second thing, we need to multiply with z factor. So to do that thing, we need to take these expressions y of z in terms of x of z. So what is the thing? First thing we need to do, we need to multiply this particular factor with given coefficients. So by giving the given coefficients, we can write the filter response of that particular filter. So we need to write that particular response. So in order to do that, what we are doing, we are multiplying with the factors. So we do have the factor value. So first thing, I'll write the factor value, then I'll try to write the output response of this given conditions. So here I do have these output response, right? Complete output response, I'll take it, then I'll try to realize it. So we do have that y of z. Next thing, we need to write the y of z in terms of this given filter coefficient. So what we are doing, students, so we got y of z, right? So after getting y of z, we need to multiply the given factors. So first we do have y of z. So y of z we'll write as it is, and we have x of z. So we'll multiply with x of z. So for doing that one, I just want to find the factor coefficients by taking these responses values. First note it down this particular part, then we'll go for designing the actual y of z by considering direct 1, direct 2, all those things we have seen already. Only the thing is we need to go for realization of that particular valued function. So I'll erase this particular upper side. So this is y of z we obtain. So what we are giving students, so we are giving first input. What is the input value we are giving? We are giving the x of z, right? So after x of z, what is the first criteria? I need to multiply with the factor of z power minus 1. Likewise, I'll go for second factor, z power minus 1. Likewise, I'll go for next factor, z power minus 1. So I do have these three factors. So by doing these three factors, I need to realize this function. So for this particular part, what I'm doing, I'm giving one summary over here. If I'll give summary, what is the multiplying factor I do have for this? First multiplying factor is summary directly multiply with 1 by 2, right? So here what I'll give 1 by 2. Similarly, I'll give one more summary over here. For before giving the summary, what I'll give the next multiplying factor. What is the next multiplying factor I do have? Nothing is there means 1, right? There is no coefficient means 1. So this is what z power minus 1, z power minus 1, make it as z power minus 2 into 1. We added this thing. Similarly, next factor. So what is the next factor I do have? This factor I need to connect with one more summary. And what is the multiplying factor over there? This should be 1 by 4, right? We'll connect like this. So we're done with the first part. So this starting 1 by 3. Where is 1 by 3? We left with 1 by 3, right? So 1 by 2 is here. It should be here because there is no z power minus 1 in this. So 1 by 2 is done over there. Then 1 by 3. This multiply with 1 by 3 factor. So I'll write over here 1 by 3. Next factor I do have is after 1 by 3. Next is 1. So this is 1. Okay, correct. After getting 1, where the 1 should be multiplied? This into this with 1. We are multiplying, we are adding with the factor. So we did with this particular factor. Next is 1 by 4. So 1 by 4 is given for z power minus 3. So we have covered till this factor. What about the remaining? We had this one, right? These two factors are left out. Z power minus 5 and z power minus 6. So this is what, these are the two factors is left out. So what I'm doing, I'll take z power minus 1, right? Again I'll take z power minus 1. I'll multiply, I'll write the question here. So we had left with 1 by 3, z power minus 5, x of z plus 1 by 2, z power minus 6, x of z plus, the question is, yeah. So in this, if you do have z power minus 4 also, we can take it. So if it is there, take it down. First see the logic of it. So this 2 we left with. So what we am doing? So how many z power is there? Z power minus 1, minus 1, minus 1. It's minus 3, minus 4. So we need to take one more z value for this. So I'll connect with one more z power minus 1. It is z power minus 5. Exactly same as the previous one. What we need to do? We have to connect here summary. So what we need to connect here? We need to connect here summary. For connecting summary, what we'll do? We'll add a plus value to it and we'll pass from, what is the value here? Z power minus 5 should be multiplied with 1 by 3, right? Similarly, we had one more, z power minus 1, this one. So total how many now? 1, 2, 3, 4, 5, 6. We'll multiply all the factors and then the coefficients. What we do have is, here we do have, take one more summary and we multiply with 1 by 2, right? So this, if you want to add with that, you can connect to this. And the output, what is the output here? We can write y of z. So if they gave z power minus 4 also in this, in any condition, so we'll write that factor here also by keeping the summary. Okay, so this is the way the problem can be realized by giving conditions. So take that particular condition, somewhat it is not visible. Here it is. Y of z we took it. It's z power minus 1 with the first factor likewise we took all the values and we wrote it, the given actual function. So what is the output of right now? What we are getting the output value, students? So write down again, once again, output value. First is x of z multiplied 1 by 2. So I want to write y of z. So y of z is x of z multiplied 1 by 2, 1 by 2 x of z plus second factor. So what is second factor here? Z power minus 1, since x of z is there for this also, x of z with multiplication factor is 1 by 3, right? Plus next z power minus 1, z power minus 1 is z power minus 2. So in this one I can write z power minus 2 with the multiplying factor of 1 with x of z plus next coefficient. What is the next coefficient we do have? X power minus 3 x of z. What is the multiplying factor here? It is 1 by 4 plus, if at all you do have z power minus 4, so you need to write this some somewhere in this. So since we don't have, so z power minus 5 we are not writing, we are mentioning directly z power minus 5. So z power minus 5 x of z into 1 by 3 plus last factor is 1 by 2 z power minus 6 into x of z is equals to y of z. This is the way the given condition problem can be solved. So in the problem z power minus 4 is also given, that I have missed here. So z power minus 4 is also given. So what we will do, students? So z power minus 4 is where it will come here, plus of 1 into z power minus 4 is there with x of z. Okay, so what we will do? We need to add over there sum and we need to multiply with the factor of 1, right? This will get it. So output value you can write y of z here, or if you want to remove the output from there, what we can do it? We'll take this summer and we'll write is equals to y of z by taking the summer from this end. Okay, we can add like this also. So by taking the summer from this end, and that's it. So we can continue with this way or that way, previous way. If they gave z power minus 4, we can write it down that z power minus 4 factor to this given question. So we do have the second concept, that is nothing but finite word length. So we need to go for finite word length in DSP. What is the use of this finite word length? So basically, what is the meaning of finite word length? That means when we are considering the digital signal processor or any kind of normal traditional computers, we need to go for the bits. Whatever the bits we are taking, the bits should be either zeros or ones, right? That means whatever the numbers we are converting or doing any kind of numbers, we need to make that n number of bits into a very finite one. That means you should know the lower value, you should know the upper value. That means when you want to find the number of bits when you're passing to a traditional computer or digital signal processor, that needs to be truncated. Truncated in the sense, if you had infinite length of bit, infinite length, we need to make it as finite. Means what? Whatever the bits you had, suppose you are having 0 1 0 1 0, this keep on going in a positive in this direction. This bit, what I am doing, I am considering this part. This is called truncation. Truncating or truncation. What is the meaning of this truncation? Truncating means what? You are making that infinite number of bits into a finite one. So while you're doing these things, you may have some sort of concepts. That concept is called quantization. So you may get this concept in your communication subjects, the quantization, right? Quantization, what you'll do over there, you had a continuous number signal that you are making into a discrete signals, right? When you had a continuous signals, suppose this is your sine wave. When you had continuous sine wave, this sine wave you are making into a discrete one. At every number of interval of time, you want to make into a discrete particular form. So when you are doing this into discrete form, so this is what actually, this is called it as truncation. Truncation, or it is nothing but quantization. So this quantization we will get in three forms. What are the three forms? In this finite word length, the basic concept of finite word length is that in digital signal processing algorithms, it is used to realize the functions with special purpose digital hardware or program hardware. In both the cases, it is going to take the coefficient and store into a registers. So what is that registers means? The registers means what? storage concept. What is that storage means? Whatever the bits we are having, we want to store in a specific format that we are considering as a registers. In that, whatever the bits we are passing, these bits are going to store in registers, right? Whether it is digital signal processing or any other processor, or if you had 8086 microprocessor, everywhere we'll use the registers. So registers means what? It's going to store the bits. Whatever bits we are truncating, those bits is going to store. So what is this truncation? Is nothing but rounding off. Round off. So round off means you want to write approximate value, like if you had in a max 128.856.013 like this there. So you want to write the approximate for it. So what you're doing, you are reducing every step. 85 is there, 6 is there, 0 is there, this is less than 5. So we will write next bit is don't change, it will be 1. This is also less than 5. So 12.8560, because it's less than 5 will not change. Next consecutive bit, that is also same. Again we want to reduce it, 8.56, this is also less than 5, it will be 6. So likewise 12.8, this is greater than 5, so we'll add plus 1 to corresponding bit, it will be 6. Likewise 12 point, this is also greater than 6, so we can write 9. So this is also greater than this is approximately 13. What you're doing, you are reducing the length of the bits by rounding off the bits value. So what I'm doing, at every stage I want to round off these bits, right? This is decimal form. So you know the number systems, right? They may be octal, decimal, binary or anything. So when you want to round off these bits into a finite length, specifically in our digital signal processor, we had a concept called finite word length. So in that we may get 3 kind of concepts. So the concepts which we are dealing with, input quantization error will get product quantization error and coefficient quantization error. So first input we are getting input quantization error will get, second will get product quantization error, and third will get this only, the registers what we are considering, those registers quantization error will get, that name is coefficient quantization errors. So when we get these kind of errors, so when we are reducing the bit length, so when I am getting these kind of errors, this is what coefficient quantization errors. So to eliminate these errors, we are going to round off the bits. So while we are round offing the bit, we may have 2 types of bits. One is unsigned bit, which don't have any sign. Another is signed bit. Signed bit means what? Those have sign like minus value. So how the signed bits and unsigned bits are going to use in finite word length, that particular thing, and how it is going to work, and what is the use of this rounding of the bits, those things we will see in the next class.